Welcome to a video on the MOSFET small signal model. So, we will be looking at the DC and AC differences or purposes for the MOSFET. Okay, so the different analysis. Then we will look at the MOSFET as amplifier, so the Q point and the linear region. Then the small signal model that we will be using for analysis and design, and we will be using both hybrid pi and the T model. Um, so we will also look at the MOSFET output impedance, or some people rewrite it to resemble the same thing as the early voltage, and lastly the transconductance. Okay, so the purpose of AC analysis is to determine the amplification parameters using the Q point. Okay, so this is to get to the amplifier gain, input and output impedance, and also your maximum inputs and your output swing capabilities of your amplifier. DC is only for biasing the amplifier at a specific Q point, or for the MOSFETs to get a specific transconductance out of it, and then doing your amplification. And the big warning here is never to mix your AC and DC analysis. People tend to get confused with some of the things, and that causes issues later on. So do your DC analysis, draw a line, just take your drain current or your Q point forward and do your AC analysis. Okay, then if you want to be a good designer, you need to know your AC and DC properties very well. Okay, because you will be using um, your AC and your DC knowledge simultaneously when you're designing. Right. So first up, our MOSFET has a Q point, and if we want to use it as an amplifier, we need to have it in the saturation region. Okay, so right here in the middle somewhere is where you will be choosing your Q point. Right, so that is why we always choose it in the middle. For the MOSFET, you can choose this slightly at a higher value to compensate for the VGS minus VT that you're having. But typically VDD over 2 is the normal go-to for most people. So VDD over 2 is kind of fair if your VGS or your overdrive voltage is very small. So if your overdrive voltage is 0.2 volts, it will be sitting way down here, and VDD over 2 would be a good estimate. Okay, then here in the saturation region, we can see that our amplifier looks kind of linear right here in the middle, and that is what our model will be based on. Right, so you bias it at a specific VGS that gives you a specific VDS value right here, and if you insert a small signal, you will get out a larger signal that is inverted. So the gain is the delta VDS over the delta VGS. So the small change, the big change here divided by the small change right there is your gain. And note for input voltages, so this small or the delta value should always be much smaller than your overdrive voltage. Some references will say 20 millivolts peak, other will say 20 millivolts peak. It depends on the size of your overdrive voltage. So you picked your overdrive voltage divided by 10. That is your rough estimate for a peak value that you can insert on your amplifier. Right. So for a small signal model, first thing, the MOSFET is a voltage controlled current source. So that gives us um, the clue to how we should build our model. So voltage in, current out. So some form of a voltage accepting over to a current source. Right. So VGS controlling ID is a transconductance. Luckily, we have defined our MOSFET as a transconductance already. So this makes a model for our MOSFET very easy. We just need a transconductance which is not um, the Kn of our MOSFET, but rather the Gm that we will be using in the model. Since it's a current source, it will have some form of output impedance. So the hybrid pi model will be the perspective from the gate. R pi is what we used in BJTs, but R pi is an infinite impedance for the MOSFET, so this will be left as an open circuit in our model. Our T model is the perspective from the source, and 1 over Gm would be our input impedance from the source. Right, so here is our hybrid pi model. We just leave out this resistor, but VGS is sitting across this open circuit. And as VGS changes, it gets multiplied by our transconductance, and that is our hybrid pi model. Very, very simple. Okay, our T model is when we are looking in from the source, we see 1 over Gm. Typically here we have Ig is equal to 0, so this is for all intents and purposes kind of a 0 point. So there's no current flowing in here, and we don't really see beyond this point backwards. Okay, this is a 0 point when looking from this side, and nothing happens coming in. So you just need to remember that for the model, when you use the model, is that there is infinite from this side, like that model. Okay, so the output impedance, if we are in the saturation region, we can extend these lines back like we did with the BJT, and they will all meet in the same point, like the early voltage. And for the MOSFETs, this is related to the channel length modulation, or lambda. Okay, lambda is usually a very small small value, something like 0.001 per volt is the unit. So that is where the early voltage comes from. So some references will use VA as 1 over lambda. The easier way would just be to say that your output impedance is 1 over lambda IDQ. Okay, so the Q point current multiplied by the channel length modulation right there, and that will give you your transistor output impedance. Okay, so this is the long-winded way that you will find in some places. But this is to show that there is a kind of a relation to the BJTs for VA. Right. Now, the transconductance. We have this region here that is almost linear, and it is the relation between our drain current and our VGS voltage. Um, so there is three transconductance equations that you can use for the MOSFET. So first is the transistor transconductance multiplied by the overdrive voltage. So if you calculated VGS and you know VTN, you can easily calculate the transconductance from that. I typically use this one with the drain current, so the root of 2 times KNID. And you can also use 2 times the drain current divided by the overdrive voltage. So there is three equations to determine the transconductance of a MOSFET. And that is it for the small signal model and AC parameters of our MOSFETs. And I will see you in a next video when we will do some analysis of the three different amplifier configurations of the MOSFET. Thank you for watching.